Now, believe it or not, some functions have zeros that are not real numbers. And in order to find the zeros of such functions, we need to consider and introduce a new number system, the complex number system. So to get us started, let's begin with something that we already know. Now, we of course know that the square root of a negative number is undefined in the real number system. Now, for example, we could say the square root of -1 is not an element of the real numbers. Now, why, you might be asking? Well, this is not a real number for the following reasons. So we know that the square root of -1 is not a real number because there exists no real value x such that x squared is going to be equal to -1. So with this equation, we can rewrite this equivalently as follows. So taking our equation here, x squared is equal to -1, if we add 1 to both sides, we have the equivalent statement that the equation x squared plus 1 equals 0 has no real solutions. Now let's take this equation here and put it into its equivalent function form. So we can say that we have the function f of x is equal to x squared plus 1. And jumping over to our coordinate plane here, we know that we have the parabola or squaring function shifted up 1 unit. So here is our vertex at the ordered pair 0, 1. So observe here, this function f of x has no real zeros or no x-intercepts because it's never crossing this x-axis. So we can say that our function f of x has no real zeros, and this is because we have no x-intercepts. The graph of this function is never crossing the x-axis. Now, with these two statements here, how do we solve for the zeros of functions like this or equations like this? Well, in order to find the zeros of such equations, we need to introduce a new non-real number, the number I. So the number I in the complex number system is defined as follows. We can say that I is equal to the square root of -1, or if we take this and square both sides of the equation, we have the equivalent form I squared is equal to -1. So this number I, this non-real number I, is going to allow us to solve equations of this form and find non-real zeros. So now that we have been introduced to this new non-real number I, we are officially ready to define complex numbers in our new complex number system. Now, a complex number is going to be defined as a real part plus or minus what we call an imaginary part or a multiple of I. So we define this as follows. So we say that a complex number is a number of the form a plus bi, and this is such that a and b are real numbers. Now, looking at our complex number a plus b, we say that this term a is called the real part. And we say that the term bi is the imaginary part. Now, notice here that both a and b are elements of the real numbers. So with this in mind, we know that both a or b or both could be 0, which is going to produce different cases of complex numbers. So in case 1 here, let's consider if we let a equals 0, what happens to our complex number? So we can rewrite this as 0 plus bi, which of course simplifies to just b times I, the imaginary part. So when we have a complex number of this form, we call it a purely imaginary number, or a pure imaginary number. Now, let's now think about case 2, where we're letting b be 0. So plugging b equals 0 into our complex number, we have a plus 0 multiplied by I, which leaves us with a. Now keep in mind, a is the real portion. So what case 2 is telling us is that every real number is in fact a complex number as well. And last but certainly not least, let's think about case 3 here, where a does not equal 0 and b does not equal 0. So in case 3, we're simply working with the complex number a plus bi. And in this case, this type of complex number is often referred to as simply an imaginary number. So now that we have introduced ourselves to these different types of complex numbers, as well as the number I, we're ready to perform algebraic operations, which I'm happy to report are going to be consistent with what we know and love from the real number system.